Hello there, students. I'm Professor McCallum. Today, I'm going to talk about Chapter 3, which is matter, states of matter, mixtures, and so on. So take yourselves some time, a second or two, to familiarize yourself with the way I have this set up. It's a little bit different than Dr. Zhao and a little bit different than Dr. Ashtarai, but overall, it's pretty much the same thing. And I will also be editing some things into the video. So as an example of that, what I'd like to do is start with just showing who today the video is sponsored by. Willie. Willie is my classroom assistant today. Willie is tired from chasing the balls in the yard. I don't think we'll be hearing from him today's lecture. What do you think? Okay, so let's get started. Today, what I'm going to be going over sections 3.1 matter, 3.2, let me write this down, 3-2, which is physical and chemical properties and changes. We'll be going over 3.3, which is elements and compounds. 3.4, which is mixtures and pure substances. And 3.5, which is separation of these things, very important things. So let's start off by talking about matter. What is matter? Well, matter is stuff. What does that mean? Matter is anything that has mass and occupies space. And sometimes you need both of these things to describe matter accurately. So for example, a gas, very difficult to weigh, and it may even seem massless, even though it isn't. We might have to think of some clever ways to weigh a gas. Right? Of course, a gas is not massless. You can condense it into a liquid, and then you could be able to weigh it. And it actually occupies different amounts of space depending on that, right? But it does definitely occupy space. In other words, a balloon, right? A balloon definitely occupies some space, right? So the matter is generally accepted to exist in 3 states, right? Solids, liquids, and gases. So there's some interesting classifications with these things that we can talk about a little bit. One of the things that we're seeing nowadays with these is sometimes the liquid and gases together are considered to be this fluid phase. And we'll talk a little bit about this a couple times during the semester, I think, and it'll be clear why we do this. So in some ways, liquids and gases are similar. In other words, they both can flow, right? You can a gas can leak out of a tire, and a liquid can be poured out of a glass, and both of those are different ways that these things can flow. On the other hand, the solid and the liquid phase are related by having similar densities. So in some ways you might characterize these things, the solid and the liquid state, might be very similar. Structurally, they're actually very similar too. A liquid and a gas structurally not so similar, but in a physical description of how they might flow, they are. So this is kind of an interesting interesting way to think about things. And this will come up from time to time. I want you to be aware of that. Okay. As an example of the states, we can often use water. Water is a very convenient reference, right? Water is ubiquitous. What does this mean? It means it's everywhere, right? That's basically what that word ubiquitous means. If we ask you to describe water, everybody can really describe water. It's wet. You can drink it. It's a liquid, and so on. So it's a very common thing. It turns out water is a little bit unusual in a number of ways, and we don't notice this because we are so familiar with water. But let's talk about the three states as we apply them to water. We can look at these states kind of in a microscopic view. So what we have here underneath these three flasks are a microscopic view of the macroscopic state. So the macroscopic state might be ice cubes, liquid water in the bottom of the flask, and then finally in the gas phase, it looks like nothing's there, but it would be water vapor over here, right? Water vapor. Now, if we do the microscopic view, then what we find out is that ice has a very, very organized three-dimensional structure, right? This is called hexagonal. You might hear the word hex in the word hexagonal. That means 6. And if you look here, you can kind of see a hint of that, right? Here's a hexagon. Maybe I should pick another color to show that, but here's a hexagon, right? Okay. So, and this is a very organized structure. In fact, this is the reason why you may know that when ice is formed from liquid, when liquid freezes into ice, the volume increases. We say ice expands when it freezes, or water expands when it freezes, and this can cause a lot of problems in winter in the Midwest where I grew up. On the other hand, water is a little bit more disorganized structure, right? It turns out the density of these two states is very similar, though. So as I said up here, if we want to characterize this through the density, we might find the solid and the liquid state of water are very similar. Now, on the other hand, steam or water vapor is a gas. And the thing about the gas phase, is we find that the density is about 1/1000th the density of the other two phases. Now, so what that means is that if we take these circles here in this cartoon as a representative space or volume, and that would mean that there would be about 1/1000th as many water molecules in the steam picture as in ice or water. And of course, we can't do that, right? Because we wouldn't even see any. 1,000 less than 60 is 0. So this is just a cartoon, right? When I refer to cartoons, I mean a picture that's based in physical reality in some way, but we're making accommodations in some way to be able to explain what's going on. So the accommodation here is two things: that steam is not very dense, right? There's not very many water molecules per unit volume, and this is supposed to show some movement, right? These two water molecules are supposed to be zipping around a little bit. All right, so that's kind of where that picture comes from. It's kind of a useful picture. So let's describe these states in a little bit more detail. Solid state is rigid, right? That means it doesn't change shape. If we go back up here and talk about the flow, if we stick an ice cube on a desk, right, and it's cold enough, if we put an ice cube on a desk in a freezer, right, to make sure that the temperature is cold enough that the ice doesn't melt, the ice cube is just going to sit there, right? It does not flow. It has a fixed volume and shape, right? Some examples would be an ice cube, diamond. There's a lot of different solids you can think about, right? And what we're sticking to here, and you probably didn't notice this so far, is our examples are going to be what we call pure substances, and we'll get to this a little bit later. What this means is that I don't want to use wood as a description of a solid because it's not a pure substance, it's actually a mixture. Okay, now let's think about a liquid. On the other hand, liquids have the property where the volume is fixed, that has a definite volume, right? We can use a measuring cup or a graduated cylinder to measure out a volume of liquid, and we can be assured that tomorrow, if we measure out the same amount, it will be the same amount. So in other words, the volume is definite. However, water flows. It assumes the shape of the container, right? So you might have a measuring cup. One day you might have a graduated cylinder. A measuring cup might look like this. Excuse my drawing, right? A graduated cylinder basically looks like this. It's kind of tall and skinny, but the same amount of water is going to acquire the shape in these two containers. And this, of course, here's a better picture, right? My drawings are kind of lame, but here's a better picture. And here we have the interesting effect that it doesn't matter what the shape of the container is. This is just kind of an extreme example of my cartoon that I drew over here, right? We have these different funny shapes, and the level of water is the same across all of them. This has a little bit to do with the pressure. So when we talk about gases, we may come back to this picture or talk about a little bit more. So liquids now, gasoline, water, alcohol, blood, these are all examples of liquids, but it turns out that two of these are pure substances and two of them are mixtures. So maybe now you can start thinking about what's different between gasoline and alcohol, right? You may know that they're both kind of hydrocarbons, right? Hydrocarbons burn, for example, you can use them as fuel. But alcohol is a very particular kind of hydrocarbon, but gasoline turns out to be a mixture. And blood, you may know, of course, is a mixture. Actually, blood's pretty complicated mixture. So you can start thinking about this, and we'll talk about mixtures in a little while. Right? All right, what about a gas? Well, a gas is kind of takes this liquid example to a little bit more of an extreme. There's no fixed volume or shape. It takes the shape and volume of its container. In other words, it expands in 3 dimensions. Gases expand in all 3 dimensions. Another way to say this is, I've heard people say this, it's not exactly true, but it's mostly true that gases are not affected by gravity, right? Here's some examples of some gases. Air. Air turns out to be a mixture, if I kind of follow along with what I'm doing so far. Helium turns out to be pure, and oxygen is pure, right? Now, the nice thing about gases is we can use one set of descriptions or laws to describe the gas, whether it's a mixture or a pure substance. And of course, we'll learn about that a little bit later when we talk about gases. So that's kind of cool. Okay. All right. So that ends section 3.1, very general description about matter. Let's talk about now about physical and chemical properties, physical and chemical properties. Well, what's the main difference? A physical property is essentially something that you can measure or observe, and you don't have to change the stuff. Now, we haven't defined what stuff means, right? So I'm using this very generic term, stuff. And as we get into this, we'll use more detailed words about this. But right now, let's just talk about some stuff, some matter, right? And if we want to know about this stuff, we might want to know about its physical properties. In order to observe the physical properties, we do not need to destroy or change the stuff, right? We take the stuff, do the measurement, and when we're done with the measurement, the stuff still is there the way we left it before the measurement, right? This has characteristics that are directly observable, right? And unique to a substance. In other words, we can use these to identify a substance. They're not, just because you measure physical property does not necessarily mean it's unique, but there's at least a chance. And for many physical properties, they are indeed unique. Okay, if that makes sense. Odor, that's a good one, right? A lot of things in chemistry are smelly. And I think a lot of emphasis is placed on things that don't smell very good, but there's a lot of things that do smell very good, like esters. Esters are a form of a compound that give lots of fruits their odor. Color is another example. Volume, right, might be a physical property. The state, in other words, the solid, the liquid, or gas, we can tell if something's a solid, and we don't have to destroy it to be able to tell if it's a solid. The density. What's the density? Now, let me erase this here. The density, we'll find out, is defined as the mass of the substance, the sample really that we have, over the volume of that sample, right? Other things would be the melting point. Sometimes we call it this MP. The boiling point, BP. BP. This is temperature. So this is kind of the temperature itself is not the physical property. The fact that it melts or boils at a certain temperature is the physical property, if that makes sense, right? If we melt some ice, right, we can measure the temperature of what the ice melts, but then we can always refreeze it, right? So we're not destroying the substance. We're changing the state, but we're not destroying the substance. This is kind of a neat picture. This is gallium, which is a metal, and it turns out its melting point, I think, is about 35 degrees, 35 degrees C, and it turns out the body temperature is 37 degrees C, right? This is a good number to know. 37 degrees C is body temperature. So your hand is a little bit warmer than the melting point, and this hunk of metal, gallium, will melt in your hand. That's kind of cool. Okay, so those are some physical properties. Chemical. What are chemical properties? Chemical properties are properties that really are based upon the substance's ability to form new substances, right? So there's going to be some reaction going on to be able to observe the chemical properties, right? So this changes. Sometimes we would say it destroys the stuff. In order to observe it, we have to destroy. Destroy is kind of an angry word, right? So let's say change. Lots of times the chemical reaction produces something you want, right? So even though you're technically destroying or using up what you start with, it's not a bad thing because you're getting something out of it. All right. Some examples of these. This is a very kind of generic, non-specific property. Flammability, right? How flammable is it? But maybe we can use a little bit more technical term. The flash point. That's temperature of ignition, right? In other words, what temperature will this stuff spontaneously ignite? Many substances are very volatile or flammable, and they have a low flash point, right? Rusting. Rust is a chemical reaction, right? We can write a very generic chemical reaction. We're a little ahead of ourselves here, but we can say iron goes to rust, right? That's a chemical reaction. The iron is not really usable anymore once it rusts, or at least the part of the iron that rusts. So we've destroyed the iron, right? Digestion of food. This is a chemical process. It's internal to our bodies, but this is really how we get energy from food, right? There's a series of complex chemical reactions involved. Some of them are kind of precursors, right? Like chewing your food. That's a mechanical process, but the first stage of digestion is softening your food and making a big mush in your stomach so that the other things in your body can digest it. Right? So these are chemical properties. So chemical properties, to recap a little bit, chemical properties, in order to observe the chemical property, you're going to change the stuff you started with, a chemical reaction. Physical property, there's no change in our stuff, right? So this might be a good point to do a little bit of a review to talk about what we've done. Okay, so after that little review, let's move on, continuing section 3.2. Let's try to classify these things as physical or chemical properties, right? So I have ethyl alcohol, that's a particular kind of alcohol that's in distilled spirits, beer and wine and so on. Ethyl alcohol boils at 78 degrees centigrade, right? This is a physical property because once this ethyl alcohol boils, if we're careful, we can capture it and condense it and we won't lose anything, right? If it boils out into the air, then we've effectively lost it. But that doesn't mean a chemical reaction. That just means we've lost track of it, right? We have to think about that.
Okay, I've actually just connected my AirPods, so the sound may be getting a little bit better all of a sudden. So let's talk about the hardness of a diamond. If you can imagine a chunk of diamond, right? A chunk of diamond, this would be a pretty big diamond. But if you're measuring the hardness, you're basically seeing how much it's able to scratch or destroy or cut something, right? Now, this is a little bit confusing because in the process, if you think about a diamond used for a drill bit or something, if you're drilling a well, then it might actually break apart into pieces, but those are just smaller pieces. We're not chemically changing the diamond. We're just maybe breaking the diamond up into smaller pieces. So the hardness of a diamond is a physical property. Now, sugar fermenting to form ethyl alcohol, this has been around for ever since the dawn of time, right? And animals were the first to discover that sugar actually fermented, fruits and so on, fermented to form a new thing that was like a fruit mash or beverage, right? That even elephants and horses and so on discovered this and got a little drunk, right? So sugar fermenting to form ethyl alcohol is a chemical process because the ethyl alcohol is chemically different from the sugar. So that's a chemical property. Okay. All right. So associated with chemical and physical properties are chemical and physical changes, right? So if we say that the boiling point is a physical property, the boiling is the physical change. And again, let's write a real simple reaction, right? If we take some water, right? This is a liquid, and we can change this to steam. This simple reaction describes the physical change that we could measure the physical property of. And this happens, of course, at 100 degrees C under normal atmospheric pressure, 1 atmosphere pressure, right? So water and steam are both water, right? You probably know the formula for water is H2O, right? So I don't think I'm giving anything away there. And so we have water H2O before, water H2O after. So this is a physical change or the observation of a physical property, right? And again, all we're doing basically here when we go from water to steam is we're pulling the water molecules away from each other, right? And the water molecules are right next to each other, right? They can hang out together and socialize. But in the vapor state or the steam state, they're much farther away from each other, and that takes energy, as we'll find out, right? So that's the physical change, the physical property. Chemical change, right? Changes the stuff, right? So we're going to have a chemical change or a chemical reaction associated with our chemical property or chemical change. Now, this is a little bit confusing because up here, we wrote this physical change in terms of a reaction, and we do that a lot in chemistry. We can use a chemical reaction to represent either a physical or a chemical change, but the chemical reaction kind of way we write things and so on is really meant to describe a chemical change. So for a Bunsen burner reaction here, what happens in a Bunsen burner? In a Bunsen burner, what we have is we have some methane. You may know that this requires some oxygen to burn. So the reaction we get is carbon dioxide plus water. And we haven't really learned how to work with chemical formulas, so you might know the chemical formulas of all these species right now, which is great. But for now, let's just put it in terms of the word descriptions of what they are. And we can see that methane and oxygen are very different than carbon dioxide and water. For example, a methane-oxygen mixture is flammable, right? It can catch fire or even explode. But if we have a mixture of carbon dioxide and water vapor in a container, and we throw a lit match into this container, nothing will happen. So just from the evidence, right? We're going to be talking a lot about evidence of a chemical reaction or potential chemical reaction. We would see it there. Another way to illustrate this is electrolysis of water. Right? And this is a very interesting reaction. You have this funny looking piece of glassware. We have this in the department, but of course I can't show you right now. And you fill it with water through the middle here. And it's a funny upside down burette. You might know that this kind of apparatus is called a burette, right? But it's upside down, right? And what you do is you open up these two stopcocks and you put water in it through the middle until water runs out these two ends. And then you close the stopcock. So all you have in here is water. And then if you hook up a battery to these terminals, a chemical reaction will happen. The chemical reaction is water going to hydrogen plus oxygen. So you, of course, you know, I just wrote it down. Water is H2O, consists of hydrogen and oxygen bound together. But somehow when you zap this water with electricity, this is called electrolysis, you break apart the water molecules into the elemental forms of hydrogen and oxygen. And these are gases. And the water, of course, is liquid. Well, when the gases are formed, they bubble up and they displace the water in the two sides, right? So one thing I want you to notice here is that the volumes are different, right? This is something I want you to think about why this is and how it could be, right? So let me give you an example. I'm just going to make up some numbers. If over here the oxygen volume was 20 milliliters, then over here the hydrogen volume would be about 40 milliliters. Why is that? Well, clearly the volume of the hydrogen is about twice the volume of the oxygen. Does that mean something? It actually meant a lot to the early chemists like Lavoisier and Priestley, because as I said before, right, gases are really hard to weigh. And if you're relying on the mass of things to tell you something about your chemical reaction, it doesn't work. On the other hand, volumes for early chemists especially were very useful to illustrate the properties and principles of chemistry. So think about this a little bit, and as we learn about the principles of chemistry and some of the laws of chemistry, volumes of gases are very, very important. And this is an illustration of that. Here's a cartoon of the reaction, right? This is a little bit better than my word. This is cartoons of water molecules. They really do kind of look like that. They look kind of like Mickey Mouse heads, right? And it turns out that for every 2 waters that are broken down using electrolysis, we get 2 hydrogens and 1 oxygen. So it turns out that the volume produced is proportional to the amount, right? The volume of gas produced is proportional to the number amount, right? So this is a very important principle called the law of combining volumes. Okay. So now let's think a little bit about examples of chemical change. We did this for physical change, right? Which of these are examples of chemical change? Pulverizing or crushing rock salt. So rock salt is just big chunks of salt. Now, salt is a general term, right? If we're talking about table salt that we would put on our food, that's one form of a salt. But once when I was a kid, I tasted some road salt because I just thought it was salt. Does not taste like table salt. Not even close, right? So rock salt is just big chunks of salt. Could be table salt, could be another salt. This is kind of like the example of using a diamond, right? If we pulverize or crush rock salt, we're just making the pieces of rock salt smaller and smaller and smaller. We're actually not destroying it. It seems like we are, but what we are is we're destroying the big pieces and making smaller pieces. The microscopic pieces remain the same. Burning wood. Well, this is kind of like wood. You may know that wood's a very basic fuel, right? This is also produces carbon dioxide plus water vapor. And we can't really turn the carbon dioxide and water vapor easily back into wood, right? Mother Nature is kind of good at that, but we're not very good at it. So that's definitely a chemical change or a chemical reaction. Dissolving sugar in water. Well, this is funny, right? Because the sugar definitely disappears in water, but this turns out not to be a chemical change. And we'll see in a little while one of the ways that we can show that this is true. We're able to regenerate or bring back or separate the sugar from the water pretty easily, actually. And melting a popsicle. Well, we know melting, right? Melting is kind of a physical buzzword, right? So this is an example of a physical change, not a chemical change. So the only chemical change or reaction here is the burning of wood, right? So let's do a little bit more here. Let's classify each of the following as a physical or a chemical change. Cooking an egg, right? This could be a tough one, but let's assume that we're not making scrambled eggs. Let's cook either the white part or the yellow part of an egg, so we don't have to worry about that. But cooking an egg is kind of hard, right? Because you definitely have the egg before and the egg after.
So it turns out it's kind of complicated, right? Because these proteins are these little blobs, and when you first heat the egg, it stretches them out into long pieces of spaghetti like substance. This is called denaturization. Then, if you keep heating it, little pieces of these spaghettis attach to each other. This is cross linking, and that makes this gel like substance.
So it turns out that cooking an egg is a chemical change. If we melt iron metal, well, we start off with solid iron and we get liquid iron, but it's still iron. So that turns out to be a physical change. And we talked about rust already, right? So we should be well acquainted with that. That's definitely a chemical change. Mixing baking soda and vinegar to produce, there's a little bit of a typo there, right? Produce carbon dioxide gas. Well, that sounds like a chemical change to me, right? Because we're starting with baking soda. What is baking soda? It turns out that baking soda has a chemical name too that we'll find out later. And vinegar too. Another word for that is acetic acid. But we form carbon dioxide gas. So the word produce or form, these are kind of buzzwords or keywords for chemical reactions, just like melting or boiling are kind of keywords or buzzwords for physical changes, right? So sometimes that can help us. Chemical, physical, chemical, chemical. Good, we're right. All right. Now, let's move on to section 3. Section 3, we're going to start classifying our stuff, right? Remember I said we have this stuff, which is really matter. This is a very general classification. Let's kind of go down something that's more specific. The next kind of level of specificity we're going to get into are elements and compounds. All right, so once we have some stuff, the stuff can be anything. It can be plastic, it could be paper, it could be potato chips, it could be anything, right? That's matter. So let's try to break this down in more specific. So we might be breaking these things down, right? So what's an element? The definition of an element is a substance that cannot be broken down into other substances by chemical methods. So basically, if you start with some matter, some stuff, this is going to be made up of one or more substances. What is a substance? Well, the kind of layman's or generic word for this is chemical. So that might help you kind of understand a little bit more what substance means. It's a chemical, right? And it might be a pure substance. And if it's a pure substance, then it's not a mixture. A mixture is more than one pure substance together. It could be a separated mixture like oil and water, or it can be a homogeneous mixture, let's say like a soda, right? That might be a homogeneous mixture, one phase. So once we have the stuff, we start separating it and breaking it down into pure substances. But if we have a pure substance and we can't break it down anymore, no matter what we do, no matter what we try, then we're able to say, well, this is some fundamental piece of matter that can't be broken down any further, and we call that an element, right? Substances that cannot be decomposed by ordinary means to other substances give you an element. Ordinary means generally is accepted to mean non-nuclear. Okay, so we're not going to do any kind of nuclear chemistry here. So an example of this was when we turned water into hydrogen and oxygen, right? It turns out we need two of these and two of these. We're doing a little bit of balancing chemical equations, right? We start with water, which is a substance, right? And hydrogen and oxygen are also substances, but we cannot break these down further into anything more pure or simpler. So these are known as elements. Okay. All of the matter in the world is made up of elements. So elements are kind of the most fundamental classification of matter. Exactly how these elements occur is a little bit further classification, which we'll talk about, right? A compound is made up of 2 or more elements, right? So up here, what we can say again, let me list these out. Water, hydrogen, and oxygen, these are all substances. We could call these substances. Right? Remember I said another kind of more layman's or generic term for substance is chemical. But water is a compound, and hydrogen and oxygen are elements, right? So even though you're a substance, you could be a compound or you could be an element, but you cannot be both, right? You're either a compound or an element, right? So here's some examples, and this is introducing chemical formulas, and a lot of you already kind of know how to work with chemical formulas, but you can kind of see it otherwise. Water, hydrogen, and oxygen. Carbon dioxide, carbon and oxygen. Sugar, carbon, hydrogen, and oxygen, right? These three elements, carbon, hydrogen, oxygen, make up a lot of things around our world, especially living things. A compound always contains atoms of different elements, right? So if it's just a bunch of atoms of the same element, then we call that an element, right? We also have the law of constant composition, which is a very important chemical law. The law of constant composition says a compound always has the same composition, in other words, the same combination of atoms, right? So the law of constant composition basically says that if you have water here and you have water in Sacramento, it has the same composition, right? If you have water, we can always represent it by the same formula or combination of individual atoms. We haven't really talked about atoms yet, though, so have to be careful. Okay, so let's kind of do a self-test here. Here we have a bunch of formulas. Which of these are compounds? Now remember, a compound are 2 or more individual elements, right? So let's see here. We have hydrogen and oxygen, so that's a compound. Nitrogen and oxygen, that's a compound. Na is sodium, right? Natrium. Sodium, oxygen, hydrogen, well, that's a compound. Mn is manganese. Manganese and oxygen, that's two different things, that's a compound. And HF, hydrogen fluoride, right? One of the most interesting simple compounds we have. These are all compounds. So all these substances are compounds. What's a pure substance? I mentioned this briefly, right? But a pure substance is a way to describe a pure substance. It's not a mixture. What's a mixture? A mixture is 2 or more substances, right? Pure just means there's nothing else in it, right? So if we have pure water, there's only water. There's no sodium or any other things in it. This is kind of difficult to acquire. And actually, tap water is not pure water. It has a lot of things in it. Most of them are there to benefit or prevent us from getting sick. Okay, so a pure substance always has the same composition. It's either an element or a compound. So it's either an element or a compound. We kind of talked about this, right? Water, H2O, hydrogen, or oxygen. These are all pure substances. But over here, if we had hydrogen and oxygen together, that would be a mixture. Pure water, carbon dioxide, hydrogen, gold are all examples of pure substances, right? And a mixture is when we put 2 or more of these things together. Variable composition. Well, what does this mean? It doesn't necessarily mean that if you have a specific mixture, its composition is going to change, but we can use the word mixture to describe basically an infinite combination of these things, right? Now, remember before I mentioned wood. Wood is a mixture. It's a pretty complicated mixture, but it's made up of more than one chemical or pure substance. It's very complicated, right? A simpler example might be wine. Wine, mostly water, right? We can start thinking about what might be in wine. It's mostly water, right? It's got ethyl alcohol, right? But it also has a bunch of, let's call them flavor chemicals, right? For lack of a better word at this, right? So that might be 10 things, it might be 1,000 different things. So we've got mostly water, the next thing's probably ethyl alcohol, and there's a lot of things that impart color and smell and so on and make wine. Very interesting stuff, right? Coffee is actually pretty similar to wine. It just is the bunch of flavor chemicals for coffee are very different than the bunch of flavor chemicals for wine, and there's no ethyl alcohol in it. Now, the thing about a mixture is we can always take a mixture and simplify it or separate it, all right? Mixtures may be separated into constituent pure substances, right? So a mixture is going to be composed of two or more pure substances, and there's technically always going to be a way to take your mixture back into its components, right? It might turn out to be very difficult, might turn out to be relatively simple, but there's going to be a way to do it. So let's talk about types of mixtures. There's two main classifications of mixtures that we're going to talk about. Homogeneous, right? Homogeneous is the first type. Homo means the same, right, or uniform. So a homogeneous mixture is one phase. So it turns out for the types of mixtures, the way we classify different mixtures is going to be based upon the phase or phases of the mixture. So if the mixture has one phase, it's considered to be homogeneous, right? In other words, it's visibly indistinguishable. We don't see different regions, different colors or densities or opaqueness throughout the different parts, right? Another word for this is a solution, right? A solution is a homogeneous mixture, right? And the composition doesn't vary. So once we decide what the composition is, or we learn what the composition is, or we define what the composition is, it's not going to change. So here's some examples. Air. Air is a homogeneous solution. I'm sorry, a homogeneous mixture. Air is also a solution. Now, even now, you probably have a okay or a pretty good idea of what a solution is, and I'll bet you that it's kind of defined around water, right? So if you see water that's colored maybe blue or so on, or let's say like river water, brown and muddy, you might be okay or know that that's a solution because it's liquid or it's water. But it turns out that air is also solution because solution means homogeneous mixture. And air is a mixture of different gases and it's only one phase. It's air, it's the gas phase, right? So this is a little bit weird to get used to, but air is a solution. Another example of solution is brass. Brass is a solid solution made up of copper and zinc, right? Brass is a solution of copper and zinc. Um, this is called an alloy. Alloys are pretty interesting because you can kind of blend the properties of copper and zinc and get something new, right? Copper is a pretty soft metal. Zinc's also fairly soft, but when you put them together, you get brass, which is pretty stiff, It's good for structural things or building things with, right? Another example of a solution that probably seems more familiar to you is salt water, right? Salt dissolved in water. And this is similar to sugar. Remember a few minutes ago we talked about sugar dissolving in water? Sugar dissolving in water and salt dissolving in water in many ways are very similar. They both disappear in the water and they form a solution. The solution is the liquid phase. Or I should say the phase is the liquid phase. Hetero, on the other hand, means different, right? So a heterogeneous mixture consists of visibly distinguishable parts, right? There's going to be regions that have different densities or properties or phases, right? So let's talk about some examples of this. Oil and vinegar, a common way that you can make, say, salad dressing, pasta salad dressing or whatever, and mix a little bit of olive oil with some vinegar, maybe some spices, and you shake it up and pour it quick before it separates, right? If you add something like a little egg or another natural surfactant, you can get them to mix, and then you might not have a heterogeneous mixture anymore. You might have a homogeneous mixture or maybe an emulsion, which is something completely different. Another example, obvious example of this is sand and water, right? You can put sand and water, stir it up, but the sand will settle out, and then you'll have the two different phases, the solid sand phase and the liquid phase. Now, right about now, one of the things that's happening is in the atmosphere outside is all the fires in Northern California. So there's a lot of smoke in the air, right? And I actually had this discussion with my wife this morning about exactly what smoke is. It turns out that smoke in the air is not really what we would call a mixture. It turns out this is something we call a colloid, and it has some very interesting properties. And some of them are very bad, and some of them make it very difficult to separate. Right? There's also liquid colloids. But if you're a little bit interested in what's happening with smoke and so on right now, you might want to look up smoke and colloid into your web browser if you're very interested. Colloid chemistry is a very active field of chemistry, right? So let's do a quick review of what we learned about mixtures and pure substances, right? Let's start by trying to identify some homogeneous mixtures. Remember, homogeneous means one phase, right? Pure water. Well, pure water is one phase, it's liquid, right? But it's only one thing, one chemical, one substance. So it turns out water is not a mixture at all. Gasoline, now I mentioned this before. Gasoline is not actually a substance. Gasoline is a mixture of a bunch of different hydrocarbons. Actually, if you've seen any commercials on TV for a lot of the gasoline or oil companies, really talk about how many different things are in their gasolines, right? It's supposed to make it better, right? So gasoline is a liquid solution, right, or a homogeneous mixture. A jar of jelly beans. Well, I don't know. A jelly bean itself is a pretty complex mixture of things, right? So is this a mixture of mixtures? I don't know. I think the jelly bean itself is a mixture, right? But the jar of jelly beans is not really a mixture. So this is one of those cases. This is one of those cases where it might really depend upon exactly how you define it. Soil. Well, soil is a solid, right? It turns out there's water in there and so on. So it turns out that soil is kind of funny because soil is not considered homogeneous. Okay, so it turns out that soil is not. Copper metal, this again is only one thing. So it turns out that only, and I've already flipped the answer, it turns out that gasoline is the only thing here that's a homogeneous mixture. Well, before we move on to separations, I want to say that there's another very common um, heterogeneous mixture that might surprise you, that most of you have come into contact with. Not so much these days as when I was a kid, but milk, dairy milk or cow's milk from the store. It turns out that cow's milk is mostly water, but what it has is a bunch of suspended fat globules in the milk, which gives it its color and its ability to block light, right? You can't shine light through it. So if you get really down and deep in the milk, you would be swimming around with all these floating fat globules, right? So it turns out that milk is a heterogeneous mixture, and now probably you don't want to drink it anymore. A lot of people these days are not drinking cow's milk anymore. They're drinking all kinds of different milks, like almond milks and so on. It's probably better for you. All right. Let's talk now about the next section. Now, if we have a mixture, right? We've talked a lot about a mixture. If we have a mixture, how can we separate them? I mentioned that you can always separate them. And technically you can. Sometimes it might be really difficult, but the examples we're going to start with today are usually pretty cut and dried. Separations take advantage bear with me here a minute, of physical or chemical properties. Well, let me put or chemical in parentheses because technically it's always physical properties, although if I discuss some of these physical properties now, they would seem like chemical properties, right? So a separation is going to take advantage of some physical property of the mixture or differing physical properties of the things in the mixtures to do a separation, right? So let's consider something very simple. Let's consider Everclear. You may know that Everclear is the common name of ethanol in water, right? This is a very strong, basically like a very strong vodka, right? It's basically just ethyl alcohol and water, and it can be much more than 50% ethyl alcohol. Well, it's a mixture. It turns out alcohol and water, ethyl alcohol and water mix very well together. We call this miscibility. They mix together in all proportions, right? So how do you separate them? It turns out that ethanol, the boiling point is 78 degrees C. Water, the boiling point is 100 degrees C. So if you have a mixture of ethanol and water and you heat it up, once the solution hits 78 degrees C, the ethanol will start boiling out of the solution. But the water hasn't hit its boiling point yet, so the water stays behind. So if we can think of a way to collect the ethanol vapor and turn it back in the water, turn it back into a liquid somewhere else, then we can separate it, right? Because as a gas, right? Anyway, we'll talk about this. So there's actually a very common chemical apparatus to do exactly this. What if we have solid? What if we have some sand in water? Well, we just need to filter the sandy water through filter paper or some other kind of filter, right? And the big solid particles will stay behind and the water will come out apparently clear and dry. It turns out that you can do this with other things too. You can do it with gas and liquid mixtures too, right? So in other words, if you had carbonated water, you could use a different form of filtration to separate the gaseous CO2 from the water. typically what we just do, right, is you can open your can of soda and let it sit for a while, and it goes flat. In other words, the CO2 comes out. But if we want to do it all at once, we would have to use some sort of filtration. Here's some other ones here. These kind of seem chemical, but they're actually physical properties. Adherence to a surface. This is called chromatography. Maybe in high school or middle school you did this, where you took a piece of filter paper or some coffee filter paper even, and you soaked a pen into it for a minute or two, and then you put this piece of filter paper in something like acetone or ethyl alcohol, and it starts running, right? And like if you put a black pen in it, you can see the separations come out. This is called chromatography. Right? And this comes about because different substances, different chemicals stick to that paper to a different extent, right? So some of them are very sticky to the paper, some of them are not sticky at all. So the ones that aren't sticky at all kind of move with the acetone or the solvent, but the other ones are kind of left behind on the paper, and it starts stretching out the dye or the ink. Volatility is another one. This might be called simple evaporation. This is an example if we have sugar in water. Right? If you put a bunch of sugar in a glass of water and stirred it up and let that glass of water just sit in your kitchen, your bedroom for a couple months in Stockton, it's fairly dry. You'll come back later and you'll just see this crust on the bottom, right? All the water will have evaporated, and that leaves the sugar behind. This property is called volatility. In other words, the ability of a liquid to evaporate or boil quickly or slowly. That's called volatility. Here's the apparatus I was talking about. This is called a distillation apparatus. And so the example here in the picture is salt dissolved in water, but the initial description I gave was ethanol in water, and it works a little bit more interestingly. This actually, you could accomplish the same thing here by simple evaporation, right? Because water will evaporate, but a salt won't evaporate, right? So to me, this is not the best example of a distillation apparatus. A distillation apparatus would better be, a better example would be ethanol and water. Let me write this down, distillation. Ethanol and water. So I'm going to draw on this a little bit, right? So let's imagine in here we have ethanol and water, right? And remember, ethanol, 78 degrees C, water, 100 degrees C. So as we heat this up with the Bunsen burner down here, this will get hotter and hotter. Once it hits 78 degrees, the ethanol will start to come up. Let me write this as ETOH. That's just a shorthand that chemists use for ethanol. ETOH will boil first. Well, remember what I said? If there's a way that we could capture the ethanol vapor and cool it down, then we could collect it. That's what this apparatus does, because remember the properties of a gas. A gas will expand to fill its container in all three dimensions. And so when we get this ethanol vapor, well, the container includes, all this space down here, right? All this space down here is part of the container. And what we do in this area is we put water in and water out. There's this jacket around the container. So it's a tube and it has a jacket around it, a cooling water jacket. So water circulating around the outside. That cools this part. So let's say over here, this might be 78 degrees C, but down here it might be 25 degrees C. and 25 degrees C is colder than the boiling point of ethanol. So the ethanol condenses, it turns back into a liquid, right? And it drips here. So we collect ethanol liquid down in the flask, right? So this is really a distillation. Two liquids, a two liquid distillation to me is a better illustration than salt and water, because you could just evaporate the water away from the salt and you would get the salt over here, right? So ethanol and water is a little bit more interesting to me, right? Well, I can see why they use this example, right? Because if you put salt into water and dissolve it, and then boil the water away, you're left with salt, the same salt you started with before, right? So there's no chemical change. So maybe it's clear that there's no chemical change there. Maybe with two liquids that look just like water, it's harder to see, right? Another way to separate a mixture is through filtration. This is where you have a solid and a liquid mixed together. Now, the solid might sit on the bottom, right? But as you know through experience, right, if you try to pour the liquid off the top of this kind of a mixture, very often you lose some of the solid into whatever container you're pouring it in, right? And if you really want them truly separated, you need something to hold back the solid effectively, like spaghetti in a colander, right? You use a colander to hold the spaghetti back or separate the two. So really, on a smaller scale, we're using kind of the colander method. You stir up your mixture of liquid and solid, right? And you pour it into this funnel that has some filter paper in it. So filter paper is usually circular, and one of the things you learn in lab is how to fold the filter paper to get this. It ends up looking like a coffee filter. You stir this up so the solid and the liquid are kind of suspended in each other, and you pour it in, and you stir up with a stirring rod in the funnel too. And then what you get down here is called filtrate. It's only the liquid part. It might just be pure water, but it might be a mixture of things too. It might be, let's say, water and ethanol too, depending on your experiment. And what you do is the solid gets trapped behind in the filter paper. All right, we're just about at the end here of this lecture. Let's kind of recap what we talked about. First, we talked about matter, right? And remember, my funny word for matter was stuff, right? This is a very general classification of what is in the world around us, stuff. Well, the stuff or the matter can be broken down, subdivided into mixtures. Generally, everything that we consider to be stuff is a mixture, right? The mixture can be homogeneous, which is one phase. It can be heterogeneous, which is more than one phase. Turns out it could be three phases, right? And the way we separate these things is taking advantage of the physical properties, and we have physical methods. That separations that we just finished talking about, the separations give us pure substances, right? So our mixture, they're all mixed up. In order to get individual pure substances, we do filtration or distillation or whatever, ethyl alcohol, water, right? But just because we have a pure substance, a chemical like ethyl alcohol and water, well, we can break these down simpler, right? Or classify these in a further way to be either compounds or elements. So both ethyl alcohol and water are compounds, right? If we break these guys, ethyl alcohol contains carbon and hydrogen and oxygen. Water contains hydrogen and oxygen. If we break these down until we can't break them down anymore, we're going to get hydrogen, gas, oxygen, gas, and solid carbon. And these are then elements, right? But this is not considered a separation, remember. If we take a compound, a chemical, and break it down into the elements, This requires a chemical reaction or a chemical method. So one of the things you should be able to do is if I ask you, how do I separate a mixture? Well, you should say, well, there's going to be some physical method to separate these mixtures, right? I'm going to say, what if I want to form a compound from an element, or I want to form an element from the compound? Then you should say, well, you need a chemical process to do that. There's going to be some sort of chemical reaction that allows us to do this, okay? So that's a wrap for this short lecture. I hope it worked out for you, and I hope the examples were useful.